Everyone. My name is Tracy Lermino, and thank you all for joining us today for this SME Technical Community and Aerodef Manufacturing Satellite Session. We appreciate you taking time out of your day to attend the Pushing the Envelope on Large Bonded Structures webinar. We're excited to kick off this satellite session with a special presentation of the Composites Community Excellence in Composites Manufacturing Awards. We'll get going in just a few minutes, but I want to cover a few housekeeping items. So first, you'll recognize that a couple of our speakers are not on video. It's not unusual for organizations to restrict the use of certain technical capabilities. Second, you'll also recognize that your microphones are automatically muted. If you have questions or comments during the webinar about functionality, please use the chat feature. If you have technical questions to our panel, please use the Q&A box. Our moderator will be keeping an eye on them throughout the event and will address as many as possible towards the end of the webinar. There will also be a polling question during the webinar, and we'd love for you to participate. It'll pop up on the right-hand side of your screen. Chrome is the preferred browser for a more reliable experience. If you have any technical issues and are using a different browser, please close your browser and rejoin with Chrome. Next, we are recording this presentation. It will be available on the Aerodef website after the event for you to listen to again or to share with your colleagues. Finally, enjoy yourself. You're in for a treat. So, we're kicking today's webinar off with an awards presentation of SME's 2020 Composites Community Awards. To start us off, I'd like to introduce Lou Dorworth, Division Manager of Aberis Training Resource and SME's co-chair for the Composites Manufacturing Group Advisors. Lou, take it away.
Thank you, Tracy. I'm Lou Dorworth, co-chair of SME's Composites Manufacturing Tech Group. Along with Dick Laughlin, president of Richard Laughlin and Associates, he's my co-chair, whom you'll hear from in a few minutes. Before we present the Excellence in Composites Organization Manufacturing Awards, on behalf of SME, we'd like to express our appreciation to the volunteer leaders of SME's Composites Manufacturing Tech Group. Their names are shown on the screen now. Some of them may be in attendance at this presentation and webinar. SME's Excellence, next slide. SME's Excellence in Composites Manufacturing Awards honor those individuals and companies whose efforts and contributions advance composites manufacturing. Both the individual J.H. Jud Hall recipient and the two corporate recipients are recognized for their achievements in leadership, innovation, technology development, and applications, continuous improvement, customer service, and education and research. So today's awardees inspire us to achieve greater levels of accomplishments within manufacturing. Next slide. First, we'll recognize two companies for their innovative advancements in composites in both the small company and large company categories. Align Vision has been selected as the 2020's Small Company Excellence in Composites Manufacturing Award winner for its distinction in the field of advanced composites manufacturing. Align Vision's technologies simultaneously accelerate fabrication rates and raise component quality while generating as-built information that lets fabricators know how well the finished component matches the digital design. The company utilizes 3D laser projection for guidance of light templates in the composite manufacturing layup process, replacing physical mylar or fiberglass templates and reducing layup time by up to 85%. That's progress. Please join me in welcoming and congratulating Mr. Scott Blake, President of Align Vision, to accept this award on behalf of Align Vision team. Scott?
Thank you, Lou, and thank you, SME, for this honor. I wish I were able to be there with you in person, and hopefully we'll do this next year. In the meantime, I hope that you and your family and colleagues remain safe and healthy. I want to thank my colleagues at Aligned Vision for the innovative work they support, and I want to thank SME for being such a great channel for connecting companies like ours to the world of manufacturing. In 1986, I was a laser light show producer working in entertainment and media for companies like IBM, GM, and developing and operating laser equipment at the Olympics, the Super Bowl, and the Statue of Liberty rededication. Some of my work showed potential to use a laser projector to improve manual manufacturing efficiency by projecting templates of light based on CAD data. In 1986, all locating of plies in composite laminates was accomplished using mylar or fiberglass templates with dozens or hundreds of holes for scribing ply boundaries. I needed to know if there could be a market for an industrial laser projector for composites. So I attended the SME Tooling for Composites conference in Baltimore and described my concept to the chair. He told me he had no idea if it was a valid concept, but that if I'd write up an abstract, SME would consider having me present a paper at the next conference. In 1987, I presented laser guidance for hand-laid composites at the SME Tooling for Composites conference in Anaheim, and the response was tremendous. It led to the launch of my company and the birth of the industrial laser projection industry. Many of you have never seen a composite part laid up with templates. In 1987, no one had ever seen an industrial laser projector. Today, laser projectors are everywhere. SME was the enabling channel for laser projection for composites. Since 1987, I've published many papers with SME, each of which is a driver for improving the manufacturing state-of-the-art. This year's paper covers new applications for automatic inspection enabled by artificial intelligence based on laser projection data and optics. Who knows what we'll be working on in the future? Whatever it is, you, SME members, will be driving it. Thank you again. I look forward to many more good years working with you.
Great. Thanks, Scott. Appreciate it. Congratulations on the award. And now let's recognize the 2020 Large Company Excellence in Composites Manufacturing Award winner, the Boeing Company. The Boeing Company has been awarded the 2020 Excellence in Composites Manufacturing Award for innovative tooling and manufacture of its 777X aircraft, which incorporates the longest single-piece composite wing spar. Thanks in part to the composite wing, the 777X will allow airplanes to carry more people more efficiently and in an exceptional comfort. The composite wing spar is the latest milestone in a decade of development, design, and build of this innovative airplane family and its production system. Ladies and gentlemen, please help me welcome Jess Trossel, the 777X airframe leader, who is accepting the award on behalf of the Boeing Company. Jeff, turn it over to you.
Thank you, Lou, and thank you to the SME. On behalf of the Boeing Company, I'm accepting the award for Large Composite Manufacturer of the Year. As Lou mentioned, the 777X has the largest composite wing ever made for a commercial aircraft. The 3 aircraft that we have in flight test today have capped a decade of design and production development of an innovative production system, which has included the collaboration of numerous suppliers such as Electroimpact, MTORS, ASC, Goodell, and others in the construction of the factory and developing the manufacturing techniques, including tooling. The composite wing manufacturing system includes this new purpose-built composite wing center. It's the 6th largest building in the world by volume, and it contains more than 60 work centers that complete every process required to convert raw materials into completed wing spars, skin panels, and other composite elements. Many innovations were required due to the scale of the wing. A couple of examples include the next generation skin and spar automated lamination equipment, automated laser cleaning of the large Invar tools, automated handling and placement of uncured parts, and automated data collection for part inspection and for equipment reliability. Thank you again for the award on behalf of the Boeing Company.
Hello, I'm Dick Laughlin, president of Richard Laughlin and Associates, and the other co-chair of Composites Manufacturing Group Advisors. I'm here to introduce to you the 2019 winner of the Jud Hall Composites Manufacturing Award, Doug Decker. Doug has been in the industry for 3+ decades and made tremendous contributions to composites manufacturing, particularly in the area of large bonded structures, subject of the webinar panel, which you'll be hearing from shortly. So to keep the bird climbing, let me introduce Doug Decker of the Composites Consultants, 2019 Jud Hall winner, to present this year's recipient. Doug?
And thank you. As you might imagine, it is an honor for me to present these awards, particularly to the 2020 Jud Hall Composites Manufacturing Award, which was created to honor one of the pioneers in composites manufacturing, the late Judge H. Hall. This award is bestowed annually on an individual who has contributed to the composites manufacturing or tooling industry through leadership in the development or improvement of processes, tooling, and applications, as well as achievements in composites research, education, and technology transfer. Curtis Wilden, Technical Fellow of the Boeing Company, is the recipient of 2020 Jud Hall Composites Manufacturing Award. He was recognized for his success in the development and implementation of processes and equipment for large composite aerostructures, which most of us are familiar. Curtis is a highly skilled engineer and innovator whose ideas are used in production, saving tens of millions of dollars annually, and have saved millions of dollars in non-recurring cost avoidance over the last 10 years at Boeing. Ladies and gentlemen, please join me in congratulating Mr. Curtis Wilden. Curtis?
Thank you, Doug. I appreciate that. First, I'm honored to be able to attend today and accept this Jud Hall Award. It's a very prestigious award, and I recognize the significance of that and the importance of what it means. And I want to acknowledge the SME technical community for what they've done in making this award available and pursuing those that are continuing to push the frontier in composites manufacturing. I'm also honored here to be with my father, who's 92 years old, who kind of was the one that ignited my inner creativity by helping me work with him when I was a young youth, unique food processing equipment, go-karts, dune buggies, and the likes in the garage and in the kitchen. He taught me that the only limits of turning imagination into application was dictated primarily by your level of effort. With creativity comes failure. With failure comes diving deeper into the unknowns to make them knowns along the journey to enjoy the joy of turning those knowns into real applications. I've been fortunate to have a supportive creative environment, not only during my youth, but at my career at General Dynamics and the last 30 years at the Boeing Company. I've had the opportunity to work with the great cross sections of engineers in creating new technologies and manufacturing processes for the 787 all-composite airplane, which was a real dream come true. Be able to see creative ideas and have those be made throughout the world. It is times like this pandemic when that forces creativity. I am encouraged by the SME organization to find ways to sponsor continued education and drive passion into excelling and advancing the state of the art in composites. Again, I appreciate this award and all those colleagues and peers, family and friends that have supported me along my journey in enjoying the composites world of manufacturing and being able to see dreams come true. And I especially thank the SME committee for their diligence and for this award today. So thank you for this presentation, and I'm to receive it. Thank you.
All right, and thank you, Curtis. Your reputation precedes you, and we're very happy for you. Well deserved, and congratulations.
This concludes today's award program. Congratulations again to Curtis Weldon and the 2020 Excellence in Composite Manufacturing Award corporate recipients. Please consider submitting a nomination for the 2021 awards. There's a link to go to the nomination page within the chat section. Thank you.
Okay, congratulations. Congratulations to all of the winners. Now, let's dive into the panel. So please remember to send any questions through the Q&A box for our panelists, and we'll turn the reins over to our moderator of the day, Doug Decker. So Doug, let's go ahead and get started. The floor is yours.
There we go. I hope everyone can see the slide here. Panel discussion is called Pushing the Envelope, the Challenges and Rewards of Large Bonded Structures. I want to clarify what we mean by bonded structures here before we move into it. When we're talking about bonded structures, we are not talking about things that we've been doing for decades. Detail parts, small assemblies, and the like. Those are successful, and we've been doing that for quite a while. We're talking about moving into a whole new realm of where you are actually gluing airplanes together, skins to substructure, wings to fuselages, and things like that. It's a whole different set of challenges that we have, and with some risk. And I'm going to talk to that in a little bit. But here's the panel you're going to see. Very fortunate to have them. But before we start the introduction for the panel, I'd like Tracy, if you could pull up the polling question here. Very, very simple polling question, trying to gauge the knowledge of the audience here, anywhere from a novice all the way to advanced. So pull that up and you can vote. And while you're voting, we'll see the results of it shortly. I'd like to get into the introductions. Kay Blahoriak. Kay has been working in adhesive bonding technologies for about 30 years. In her role at Boeing, she has worked the entire building block pyramid of understanding bonded systems, from the molecular level to devising practical manufacturing methods. Her work has encompassed the validation and certification of bonded structures for both military and commercial aircraft. Kay, if you don't mind, can you say a few more words about your background?
Well, thanks, Doug. Thanks for having us all on this panel. I'm excited to join today. And my part in bonding is really that practical aspect of how do we make it achievable and robust, and make sure that we can manufacture and repair things and have competent bonded structures over the lifetime over which we expect to use them. And that's where I come from in my work.
All right, thank you, Kay. I know everyone has other jobs other than that, being on a panel, but this is valuable. Thank you. Giles Dillingham. Giles is my go-to guy on how to make sure things are stick together, let's say. He's also the person I would go to find out why they didn't stick together. Giles shares with Kay an innate knowledge of how things work from the manufacturing level all the way down to the molecular level. And Giles was a critical participant in the DARPA-funded TRUST program. Now, if you haven't heard about the TRUST program, it's one of the best acronyms ever. It stands for Transition Reliable Unitized Structures. You'll soon hear a theme among the panel members as far as being TRUST participants. Giles, can you add a little bit?
Yeah, I'll add a little bit. Doug, you did a pretty nice job of summarizing there, but I'm a material scientist by training. I've been working in surfaces, interfaces, and adhesion for 30 odd years now. And we work with basically any company any companies that coat or glue or bond or print and have problems with things sticking. And we dive down into that, again, the kind of molecular level understanding of why things either are working or aren't working. And this has led us into a lot of work in process control, trying to develop process control methodologies, trying to understand appropriate process control approaches towards different manufacturing operations. And it's endlessly fascinating. So thanks a lot, Doug. Looking forward to the panel.
All right, thank you for participating. Misha Grigoriev. Misha brings with him an industry-leading knowledge of advanced surface prep techniques using plasma treatment from his experience at Surfex. I had the privilege of working side by side with him at Northrop Grumman on large bonded structures during my time there. Misha was also a critical participant in the DARPA Trust effort. Thank you for participating, Misha. Do you have a word or two you could share?
Thank you very much, Doug. Sure. I'll say a couple of things, such as I am a mechanical engineer and a physicist by training, and I'm a small fish in a big sea, and I love turning wrenches at the company that I'm at. I do anything from figuring out how to use a paperclip to save a very expensive article to plan out dozens of years into a future, and bring the technology, mature the technology along to make sure it's ready when we need it. Thank you, Doug.
Well, all right. Thank you, Misha. Appreciate that. Bree Oakley. Bree also brings a wealth of experience on the impact of surface contamination and bond strength through her work at BTG Labs and Trust, and is now taking that knowledge to apply at Lockheed Martin. Bree, thank you for being on the panel. Do you have something to share?
Sure. Thank you, Doug. And I would say a bulk of my work in the last few years has really focused on taking those research type things that we did at BTG and understanding how best to translate that to actually building structure. So communicating what we learned on the trust program to the folks that are doing the bonding. That's a big portion of the success of bonded structure. So happy to talk more about it as we dive into the panel.
Okay, thank you. Thank you. And last, myself, a little more background information. I had over 30 years, about 37 years, working in the aerospace industry, primarily at Northrop Grumman, but I had an opportunity to work on both satellites and ship vessels and fighter aircraft and bombers. So I've seen a lot of changes going through the industry. And one of the things that the industry is moving towards is getting away from fastening airplanes together to actually bonding them together. When I started in the industry in 1981, there were programs on how to install and drill and install fasteners, and there's still programs close to 4 decades later on how to drill and install fasteners appropriately. So I'm trying to put that behind us. So I appreciate everyone who logged into this, and I have a very short presentation to walk us through here before we go into the Q&A. A lot of you have probably seen this quote before, but I'm gonna read it for you anyways. Aviation is not in itself inherently dangerous, but to an even greater degree than even the sea, it is terribly unforgiving of any carelessness, incapacity, or neglect. Now, that, if you're just talking about aviation in general, is probably true today as it was then, even though the safety records of the aircraft have improved considerably. But I take this quote and I like to just change one word on it, and like to change aviation to bonding. Bonding is not in itself inherently dangerous, no matter what people tell you. But it is not forgiving when it comes to carelessness, incapacity, or neglect in doing it. If it's done right, everything works well. If it does wrong, if it's done improperly, then not quite the same. And I think that's the general judgment of the industry and our customers. We're in a bit of a transition phase when we're talking about large bonded structures, gluing airplanes together. So I have you're probably very familiar with the risk cube, but I'm going to go over it here. The focus of a risk cube is to find the things that you have to pay attention to and put extra attention into and safeguards. On the y-axis is the likelihood of an event happening, all the way from rare to almost certain, where you know for sure it's going to happen. And on the x-axis are the consequences. If that event were to occur, are the consequences, inconsequential or marginal, all the way to severe. The worst possible thing could happen. So the greener areas where not too much to worry about. Anything outside the green is something you have to focus on. Where you're up in this category, where you have an almost certain likelihood of an event happening and a severe consequence, all hands on deck on making sure that doesn't happen. So what I've done is I've broken it down into three main categories, and you're going to see that, and I populate this risk cube with it. The design, the process control, and the traditional inspection techniques. So as far and where they fall in the cube. As far as the design goes, now that I originally had a different design in here, but the panel member, we had a group of panel members who didn't want to show risk for commercial, and we had another group who didn't want to show risk for military aircraft design. So I completely understand it. So where we fall on actually designing large bonded structures is one of the risk areas that we have to look at. As far as the process control goes, then this we're going to find out is really the critical aspect when you're gluing airplanes together, is the process control. And that is all the way from the surface prep of the structure, whether you're sanding, whether you're plasma treating, whether you're peel ply, or whatever your surface prep, all the way through the bond. Getting the right adhesive down with the right out time at the right pressures and at the right temperatures. There's a lot of effort that goes into this. And the traditional inspection, when I call it traditional inspection, are things that we're familiar with. The ultrasonic scanning, A-scan, C-scan, those kind of things, where we get detailed parts and structures, and we inspect the bond integrity. When we're talking about bonded structures, are there DLAMs? Are there dis bonds? Are there inclusions? Is there FOD detected in those? So I'm saying that traditional inspection, there are a lot of different variations here, fall into that. It is trying to prevent internal escapes where, wow, we caught something here. We have a dis bond, we have a DLAM, we have FOD, we have to fix it. But once we pass that gate and we don't find any issues, or we fix the issues we've had, when we're talking about bond strength verification, we do not know how actually strong that bond is. We know that there's maybe not an inclusion, maybe there's not a DLAM, maybe there's not a physical dis bond you can identify, but you don't know whether that bond is full strength or post-it note strength. So that is one of the challenges with our traditional inspection techniques. So how do we quantify the bond strength? And I say this preventing external escapes, meaning everything checked out and you're delivering to a customer. We really have only two categories on that. There's proof load, and there's a laser bond inspection technique. Now, proof load, you're familiar with it. This happens to show an Airbus wing being flexed. They don't do that for every tail number. This is one of the non-recurring design tests that they run. But there are programs that do actually proof load structures. Global Hawk and Triton wings, those are bonded high aspect ratio wings, and those are actually proof loaded to verify the minimum bond strength of it. Short of this is not always practical. In fact, more often than not, it is not practical. You can imagine putting a bomber or every fighter into proof load rig and flexing it. So where do we stand if we can't do that? Laser bond inspection. I don't know if you're how familiar you are with it. LBI, it puts a pulse into the surface, creates a compressive wave, comes back as a tension wave, and depending on the amount of energy that's put in there, you can have a local failure. It's a spot check for bond strength to try to find significant reductions in strength. So where do we fall on the risk chart of here? The industry knows how to design airplanes. They know how to test airplanes that are made properly and have designs that will meet the structural properties. The likelihood of having a major design problem are very, very rare. Severe if you do, but they're very, very unlikely. Now, as far as the process control, it's higher up on the Q process. There are so many processes working with so many manual operations and people. There are a lot of things that have to be done right along the way to get a full strength, robust bond. So that's higher up the risk cube for it. Got to pay attention to the process. Process is one of the biggest players. The traditional inspection, kind of know how to do that. It is unlikely that we are going to miss something significant using traditional inspection techniques, but it has its limits. So we're forced into what this can't find and controlling the process. So these are the areas to focus on. These are the areas as final quality verification. And just one or two more slides. How strong is the bond? It's how do we quantify the bond? And I like to say, well, it's kind of like a wheel attached to a car with lug nuts. How well is that wheel attached? What's the strength of the attachment? You have a brand new car delivered. It's sitting in your driveway. You haven't taken it out for a test run. It's before everything looks good. It passed dealer qualification, an inspection. The wheels seem firmly attached, all four of them. They're not tilted. They're not wobbly. You shake them and you actually hand torque the lug nuts. Everything looks good sitting in your driveway. And then you want to take it out on a high-speed run on the freeway and see what it's made of. That's when everything, if there's an issue, it will show up. Everything's good. It appears to be good until it's not. So unless there's a quantifiable way of making sure that those wheels are firmly attached to the car under the loads and inspect that, you're making an assumption. So that is the challenge. The problem is that a low strength bond looks an awful lot like a high strength bond. And this is the last slide, and we're talking a lot about risk. I don't want to give the impression that structural bonding is inherently risky, because I don't believe that's the case. But we are taking calculated risks, but not being rash. But there's something like the point in the industry we are right now is kind of changing the tires on a moving car, because we're designing platforms that we're bonding together without a fully laid out quantifiable measurement technique. So I would like to start taking some questions and to the panel. So let me get out of the sharing here. Am I unsure? Okay, where are we? Oh, okay. Well, I thought I was sharing there on that, so I wasn't. So, do we have some questions for the moderator? I have a couple. And this one I'm can throw okay? All right. Airbus and Boeing are integrating and significantly increased levels of advanced composites in their current and future product lines. How is bonded structure different than what these companies are doing? So, commercial versus large bonded structures elsewhere.
And that's for me, Doug? Okay.
Yeah. Yes.
Okay. Yeah. Well, I can speak to what Boeing's doing, of course. And, the certification approach for large integrated bonded structure really isn't that different than regular composite structure as far as the path that you travel, with the difference lying in between the details of the processing steps. And it should be noted that moving into integrated bonded structure is not really a step function, but more a design decision to make the process windows robust, inline quality steps at the critical points, and a well-defined and characterized bonded system. And you'll hear in all my answers kind of that theme of the bonded system coming across, in that you have to know exactly what you have and understand the box and elements surrounding each and every part of that bonded system, from each, from the adherent and all of the layers of the bond through the processing steps and how it'll be utilized in service. But, we do have a lot of really successful, important bonded structure, from the skin stringer co-bonds on the 787 and 777X wings, the wing spar on the 787. Skin stringer bonds are all over the place on the 787. And as well as on the military side, with historically really important bonded structures such as the F-18 titanium CFRP step lap joint and a lot of important rotorcraft bonds. So we do know how to do this. We do know some of the challenges in using bonded structure. Future products may apply different bonding processes or technology, but it's hard to imagine a greater fundamental integration of bonding than we currently have. So I'd start with that. We are increasing the amount of bonding we use over time, and there's certainly opportunities on where we might use it in the future.
Okay. All right. Thank you, Kay. I have another question. This is going to be the panel at large. The panel members are primarily focused on DoD contracts. Are there significant differences in the economics of bonding between commercial and DoD platforms?
Well, this is Kay. I can start there because we certainly have both. The quantities and rates of varying programs always play into the decision of, what to pick with respect to your materials and processes that make the most sense for that particular application. And new bonding applications will always need to, win their way onto a program based on things like recurring cost, rate, certification costs, and things like that. There's slight differences with respect to the certification requirements between the two, but for the most part, there's more similarities. The key for both certification efforts is to have a well-qualified bonded system, as I said, and have all the processing parameters in hand when the design starts, and that helps you have transition. Another aspect with commercial is there's a major advantage with bonded structure on the commercial side in terms of volume and the consistency of production. Longer production runs can justify greater investments with respect to that fundamental development and the validation of the bonding processes, and it can support greater investment in fixed cost enablers such as automation and process monitoring and things like that. So that consistent, continuous nature of commercial product production also lends itself to a consistency in the process and resulting bonding performance. Materials tend to be used within their working life. Personnel tend to retain familiarity with those processes and are maintain their skills. And you have that dedicated production environment that is consistent throughout that lifetime that limits the potential for more of those unintended things that might happen if you have a more interrupted production stage. So those would be some differences and similarities that I would say.
Thank you. Anyone else? One thing I found having to work in defense, I have exceptionally limited experience when it comes to commercial. Is commercial definitely as fuel is one of their main variable costs there. So fuel efficiency is one of the things that we'll focus on. But in military, it may very well, fuel does have to do with range, but they generally focus more on the performance aspects of it. So when we talk about bonded structures and getting fasteners off the surface, there's a big low observable improvement for getting fasteners out as well as the cost reduction. I do have another question. What are this is to the panel at large, what are some of the challenges the industry may face along the journey to successful transition of large integrated bonded structures? So we said the name of this is challenges and opportunities. We mentioned a little bit of the opportunities and some of the challenges, and there are challenges. So I'm going to open it up to what do you see are the things that the industry's headed into right now as far as challenge?
Well, Doug, this is Giles speaking here. You touched on a lot of this in your intro. Part of the big challenge is how do we get away from proof testing to a level of process control that gives us a level of confidence in these structures that proof testing is a I don't want to say superfluous, but not what we're relying on to make sure that we've manufactured a good structure. And we don't, although we're learning a lot about these process controls, and all of us are working on developing these every day, they're not in place yet. And one of the reasons that they're not in place yet is that we're still depending so much on, that aerospace manufacture is such a, particularly military, right, is such low volume, low rate manufacture. The economic drivers for automation and automated process control really, really haven't been there.
Yeah, and I'd like to add to that, and I'd like to take a step backwards, where the fact that we're building or attempting to build large, composite structures, the whole idea has changed the design, and that had a domino effect all the way down to manufacturing, to inspection, to all the processes, and trying to go through that and put that together and imagine it is a challenge on its own. Are we ready for that? How do we plan for something that we knew the small puzzle pieces, they worked, in those smaller cases, but again, putting the whole picture together, it's a tough ask. And I can throw challenges at you all day, Doug. I'm sure you know. We have, if we're bonding something, it means we're raising temperatures, and if we're raising temperatures, we have to prove that we raise temperatures to the correct specifications. We're likely trying to raise them across large surfaces, long, and now we're talking either extremely large methodologies, and how do you do that all simultaneously to ensure a cohesive type of process? So there's variable geometry comes into play. You're fighting physics half the time. So you maybe some of the sequencing that you planned ahead involve metallics that you can't raise the temperature up on. So again, we can really dive in and talk about every one of these little pieces, but at the end we're trying to get a full structure that we believe in. And I think like Giles said, that's we most of us are playing in small numbers still, and until we get to experience of one or two or five of these types of projects under a belt, I think we're going to have to be discovering and rediscovering and inventing new technologies to help us along.
Okay. All right. Thank you. Another question that came from the audience. Are there systems in place to allow re-inspections of airframe bonds to be compared to baseline OEM inspection results to show rate of degradation? So delivered a good one. You flew it around for a long, long time, did terrible things to it. How do we know it's still good?
Take it apart and look at it.
Turn the key to the turn up. Yeah.
This is the sort of driver that really makes us look to techniques like laser bond inspection. If that can be made practical, what a wonderful tool that could be for monitoring structural health.
I think that's a good point. There are other ways of monitoring structural health, such as active ones, placing either some kind of a strain gauges or fiber optics into your entire body, and maybe monitoring that during flight and during the life of the article that you can record and review. That's right. That's an idea.
Yeah, I would concur with those statements. I mean, the methods that we have for inspecting aircraft today and the health of the bond are typically things like visual inspections, changes of shapes, or obvious delaminations, and using traditional NDI to see kind of that after effect when the bond is at a state where you do have a significant amount of degradation that you can observe. And And for bonds where you can't observe degradation, we do things for the design to account for that. So there will be a different design philosophy on how, many chicken fasteners or other design features that you put in to ensure that you've got redundant structure in those places that are not inspectable. There's been, I'm super excited for the team that is working the laser bond inspection, because the maturation of that process in the last 5 years or so has just been remarkable. So, that's going to be an important tool for not only helping us validate original structure as part of the process control methodology, but also to assess and understand structure that's been fielded, bonded structure that's been fielded on the field. There's some work to do with respect to how do we perform that, with accessing the bonds that you need to, the areas that you need to see, and miniaturizing the system such that you can take it to where it needs to be used. But it's sure looking exciting, and I'm eager to see how far we can bring that.
Thank you. Anyone else before I get on to the next question? This one's going to go to you, Bree, I think.
Okay, thanks.
All right. The DARPA Trust program went through a multi-year extensive investigation into the variables impacting bond strength. What, in a nutshell, do you feel was a primary takeaway from that effort?
Well, I really think that the primary takeaway from that effort really kind of echoes back to Kay's statement of a well-characterized system. At the beginning of that program, we tried very, very hard to make a bad bond. We have this specter of failed bonds kind of looming over us, and these tales of potato chip fingers and this, that, or the other sort of bond preps. But when it came down to the real work, it was very hard to make a bad bond. So if you can characterize your system, and so it's like Kay was saying, system, your substrate, your adhesive, the whole kit and caboodle, you can really have a lot of confidence in moving forward with that system and bonding. For example, we found that our system was quite robust, and we had to put a lot of silicone on that surface to make a bad bond. Other systems may not be quite so robust, and you would need to have a little bit more control, but knowing that you do have a very robust system, I think goes a long way into translating that to actual bond processes that you do on the shop floor. And that I'm going to kind of pull in this question in the chat window about how you control large area surface preparation, verification, adhesive application, and joint closure within a reasonable time. I think it also goes back to having that knowledge about your system. For our system, because we did transition to a peel ply removal surface prep, we were able to kind of characterize, okay, well, in this controlled environment, how long is it good? And then we cut that window off at a reasonable time frame. And that kind of, that knowledge of how long you really have with that system to work with it can kind of inform your manufacturing plans or even your design. But just in terms of, prepping as much as you could bond within the window that you feel comfortable with based on that intimate knowledge with your system. I think that's really the big takeaway, is to know your system.
Thank you. And I remember the takeaway, and I remember a quote from you. You needed silly levels of some of these contaminants to actually get a bad bond. So that may have put one or two people at ease that it's not lurking around every corner. But
we're not teetering on the edge of just completely unzipping.
We're getting near the end here, so we just have about 5 minutes left. Here's the question. How do you monitor critical bonded structures to predict failure and replacement? What are your measures of failure short of failure?
I mean, we touched on that kind of in 2 questions back, I think, right? Structural health monitoring is not real highly developed yet. We're hoping for evolution of techniques like laser bond inspection to the point where we can deploy them like casing in ways that we can access all the areas of bonded structure that need to be accessed. But this, looking at the health of a bonded structure over time is that's a real challenge. I think we don't currently today have real practical ways to do that. We might be able to detect disbonds through certain types of inspection, but we can't yet practically detect a weakening bond, a bond that is deteriorating but not yet failed over time. Now, okay, maybe you've got other comments on that or.
Well, I mean, there's a number of ways to de-risk the process and the lifetime of a important structural bond, and there's the upfront things that we do to ensure via process control, via inspections, witness coupons, LBI. There's so many different ways that we deploy to ensure that the process that was used to create the structural bond is what we think it was, and we validate that and ensure through continued manufacturing process controls that continues. Once you have fielded structure, one thing that we hang our hats on is that we have tested that particular system to in the laboratory with components, with elements, to understand what happens when it is exposed to various environments, various loads, various predictions of ways that aircraft could be used. And based off of that, we feel like we have a good understanding of the predictive nature of how that bond will perform. And a good example of that is, I think, with moisture durability. And in a metal bond, we know very much about what happens if you don't have a well-prepared surface and that the moisture can diffuse into the bond line and cause degradation of that interface. Whereas moisture in a composite bond line is quite a bit different, and you don't see that same interfacial degradation and as you would in perhaps a metal bond. We've tried many different ways to make that happen, and it just doesn't. So I think that predictive nature of torturing the specimens and elements in any ways that we can is part of how you get confidence of how that bond will perform over its lifetime.
You do your homework before you build the airplane.
Absolutely.
Yeah. And I would have to say we would never let a system out of our garage that we don't believe in that is of quality, and because we know what we're releasing out of our garage, we have a known cycle or a flight hour type of schedule maintenance that we recommend, again based on everything that Kay said with respect to our material knowledge and our scrutiny of it. I think we'd have that schedule maintenance and
and the good thing about it, composites tends not to fatigue very easily. It doesn't fatigue much, and so far we've seen with good quality bonds some of the similar behavior. We are running out of time. I'm told we can run over 5 to 10 minutes. I'm willing to take two more questions, and one of these is I think probably based on one of Bree's comments, and it's going to be thrown over the wall to you, Giles. It says, sounds like silicone is by far the most dangerous contaminant that influences bond strength. So is there a quick and practical way to identify and quantify its presence? And a follow-on question, do we know what thresholds are safe?
Right. So those are pretty pregnant questions there, Doug. First of all, a silicone is not a silicone, right? We tend to talk about silicone contamination but there's a huge range of structures of silicones, some of which are very detrimental to bonds, and some which are not very detrimental to bonds. So we can't lump all silicones together, okay? That's one important point. Another very important point is that different adhesive and substrate systems will be sensitive at different levels to contaminants like silicones. It is safe to say that silicone is the worst contaminant that I think any of us have ever come up against. Robust adhesive bonds seem to be able to deal with quite a few things like fingerprints, for example. You know, they're not as detrimental as we might think they might be. Silicones are very detrimental, but if we're looking, for example, at room temperature cure adhesives, they're very sensitive to small amounts of silicone. High temperature cure adhesives are much less sensitive to silicone. And we've got to worry about the exact structure of the silicone. So it's not one size fits all. We can't make blanket statements about it. We can say, yes, be worried about silicones, but the type of silicone and the type of adhesive system matters a whole lot. Now, in terms of detection of these, you know, there are plenty of ways to detect detrimental amounts of silicones in your systems. You know, we tout contact angle measurements. That's a great way to do it. There are other ways to do that which maybe haven't reached the same level of development in terms of deployability yet, but things like laser-induced breakdown spectroscopy, LIBS, is definitely capable of detecting detrimental amounts of silicone on a bond surface. It's not clear whether the handheld shop deployable systems are capable of doing that yet, but there certainly are larger systems that do a great job at that. NASA's done quite a bit of work in that area. There's handheld techniques like X-ray fluorescence, which can detect detrimental amounts of silicone on surfaces, as long as you don't have other sources of silicon in your material system, like glass fiber reinforcements or quartz fiber reinforcements, for example. So you know, it's kind of system dependent, but we do have ways to detect those things in manufacturing. Hope that wasn't too long-winded there. But,
I'll jump in here also to say, you know, it is kind of like a holy grail to be able to detect a detrimental level of a detrimental silicone on your surface before you bond it, so you can either remediate it or bolt it. But kind of going back to that, you know your system comment, and you know your system, you'll know if you really are only sensitive to the worst of the worst. For example, like a cured mold release product on your bond surface, which you would hope would never happen. And so you can institute your process controls to, you know, prevent that from even crossing the threshold of your building, for example. And you can, you know, with that knowledge of your system, you can kind of, I guess, use that knowledge to replace the need for detection of these really, really detrimental things when you know it's, you know, something that's the worst of the worst, and not, for example, you know, silicone residue from tape, which may or may not be detrimental depending on your system, depending on the temperature of your cure, like Giles was saying. So, you know, while we can't, you know, do this perfect detection, knowledge of your system will tell you, do you need a really sophisticated detection technique, or can you be really vigilant and rigorous on your process controls and who and what you allow in that building?
All right, thank you. One more question here, and this is a kind of a global, in the theme of mentoring people. This is a good opportunity here. It says, I'm a newly graduated mechanical engineering student looking at my options for future career. For each of you, what aspects of your career do you enjoy the most, and what do you enjoy the least, and why?
got an hour or two?
Don't kill the curve.
One of the most wonderful things about the sort of stuff that we do, and I think that most of the people on this panel are involved in, is we get involved in problem solving. We get involved in problem solving in a wide range of areas. And we're talking about bonding here. Bonding touches so many areas of industry, so many areas of manufacturing, chemistry, mechanics, physics, all this sort of stuff gets involved in it, and there are problems everywhere in it. And that's really kind of what keeps us going what keeps us working in this area for 30 years, is that there's a never-ending supply of fascinating problems that are intellectually stimulating to work on and that are relevant, right? They're important.
Mm-hmm. I'll jump in to say, sorry, Kay. All of us here on this panel are from different companies. Giles and I used to work together for many years, but now I've moved on to Lockheed Martin. You get to, I guess, interact with other folks, just like on this panel, which is really fun, just to keep those connections with people who are working in your industry. And generally, you get to work with really smart people, and you get to learn a lot from all of those people. And that's just really fun. To just echoing Giles's comment, you're always solving problems. You're always, you're working with people that you learn a lot from continually. And that gives me a lot of satisfaction to, work with people I can learn from and continually learn from.
Yeah, this is Kay. I'll add on to Bree. I mean, actually, the aerospace bonding community, it's really small. So, when you've been in a while, you pretty much tend to know everyone in your network within that broader community, and that's pretty cool and fun. So you've got lifelong relationships that you build, both external to your company and within. I would say my most satisfying thing is, I'm a materials chemist, and I transitioned into, more of a material science career because I really like the aspect of building things and seeing and handling that tactile aspect of that, and being able to make a difference in, making safe structure and making our customers, our soldiers, my family members safer throughout the work that I've done. That's probably the most satisfying. I would say that you said on the other side, the most unsatisfactory thing is there's always plenty of people who find ways to say no. So it's really challenging. You want to make sure you hang out with the people who say yes, because that's a much more satisfying.
I'll give my 2 cents. Cost schedule planning is the least satisfying because we all tinkerers, we all problem solvers. Get us on the floor, give us a problem. I think that's where we shine, and that's what we're doing here.
Thank you, Misha. And I'm going to close. When I graduated from college and went into the industry, I was under the naive assumption that all smart people who took all the same classes as you took, when you get into the industry, would all agree. I could not. They all come to the same conclusion. I could not have been further from the truth. So you get smart, well-meaning people with passionate arguments that are diametrically opposed to each other. And that can be the fun part of it. Frustrating at times, but fun part of it too. So I think we're going to close. I like to thank the panel members for taking your time out of your day and supporting this. I'd like to thank everyone who attended, and I'm afraid we couldn't get to all of the questions. For that, I apologize, but thank you very much. Tracy, do you have any closing?
I do. Thank you, guys. Wow, what a great discussion and questions. I'm so happy. So thank you all. And thank you to our panelists, Giles, Kay, Misha, Bree, and of course, our fearless moderator, Doug Decker. We appreciate you all setting aside the time to be with us, supporting SME events and the manufacturing community. We also want to thank you, or thank all of our attendees who participated today in the webinar. Please make sure to join us for our next month's webinar. Registration is now open for our next panel discussion, The Next Wave in Manufacturing, Aerospace Manufacturing, moderated by Dan Braley on September 17th from 3 to 4 Eastern Time. We hope to see you then. Have a great week, everyone. Thanks.
Great. Thank you very much.
Bye.
Thank you all.
Bye.